Yes, so I start again at this place here where we were discussing this commutator estimate. So it's this functional inequality that you want to prove for general configurations, general vector fields here, V of x, general background probability density. And one of the questions is, of course, for which interaction kernels G can you prove such a thing? So so far I've explained to you that it can be done for Coulomb or for super-critical, super-coulomb Reese interactions, but it can also be done for sub-coulomb interactions. And the difficulty here is the removal of the diagonal here. So this sort of renormalization that has to be done, which consists in removing infinities, you know, that's why I call it renormalization. Because otherwise estimates of this type appear. So estimates of this type can be found in the literature on harmonic analysis. Type, but not exactly this one, of course. Are found in literature on singular integrals. Something that called Chris-Journet operators, and we will in some version of the proof, we will use a bit of these estimates. So you can look at the literature. For instance, a paper by Seeger, Street, and Smart. But it's not the first paper on that. But you can find references there. Usually in these papers, they assume that divergence of V is 0, so that the vector field here is divergence free. I think for also applications that have in mind or in fluid mechanics where you have such a divergence free condition, but here we have no reason to expect that divergence V is 0, and we will not assume it. The other thing is that I call this commutator estimate. So let's say a word about why the term commutator. So it's because when you write this quantity, so let's forget a little bit about the diagonal problem, but if you write this, V of x minus V of y dot grad g x minus y. So let me write df of x, df of y for shortcut, and I will write here f to be the difference between these empirical measure and rho. Okay, so it's a measure of integral 0. So we can write df of x, df of y. So nothing prevents us from breaking this into two pieces. One piece which is v of x dot grad g x minus y df df minus v of y grad g x minus y df df. And the first piece, I can write it as the integral of v dotted. And so here I want to write a convolution. I want to see this as a convolution. So in fact, it's grad of g convol with f. Grad g convol with f times f. And the second thing, I can write it as the integral of what do I want to do? So I want to group V and F, you see, V and F. And I want to integrate by parts. So let's sort of take the gradient onto the other parts. So it's going to be a convolution of G with the divergence of Vs You see VF, divergence, and all of that times F. Okay, so in other words, I can rewrite this as the integral of F multiplied by some big thing, which is gradient G convolved with F dot V minus G convolved with div VF. So here there is a sort of commutator, and you can see it already because you are doing some operations. You're doing operations taking a derivative, convolving with G, and applying V, but you're doing them in different orders, right? So here first you convolve, then you do derivative, then you dot with V, and here first you dot with V, then you do derivative, then you convolve. So in fact, you can do that, make this more precise, and you can write this. So this is to be checked, but it's true. As the L2 scalar product, so you see it's going to be an inner product in L2 between F and this big bracket. And this big bracket is a commutator. It's a commutator of the operation of dotting with V, doing the gradient, and convolving with G, which in this case of the Rees interactions is the same as a fractional Laplacian, right? So it's this applied to F. So you see here you have a commutator between an operator, that's this one, and the application of the vector field V. And here I remind you that, maybe I don't remind you, I haven't said it, but G, which is 1 over x to the power s, up to a multiplicative constant, is the kernel of the fractional Laplacian minus Laplacian to the power d minus s over 2. And you can see that this is consistent because, you know, in the Coulomb case, when s is d minus 2, you want to recover minus Laplacian. So, okay, when s is d minus 2, this is 2, that's 2 over 2, so you recover minus Laplacian. Okay, so this is true, and you can also check it by going through Fourier transforms. You remember what I said last time, yesterday, that the Fourier transform of these inverse powers is an inverse power itself, and that you can recognize as some negative power of Laplacian. Okay, so this is the reason for this denomination of commutator. So there is a commutator. There are some singular integrals, stuff that are related, but the difficulty here is to handle the singularities in the form of the Diracs. Okay, so once you have that proposition, if you assume it as a black box, this proposition has turned out to be useful. So proposition is used as a black box, I would say. So for our proof, definitely for mean field limit convergence. Now I've showed you that once you know this proposition, you have the Grunwald inequality on the modulated energy, and then it's 2 lines to finish. So it's really the crucial point of the proof. But it has been used also for mean field limit in the quantum Coulomb case. So not for this classical dynamics, but for quantum dynamics. So this is the work of Goltz and Paul. It's recent. So they have a quantum framework, but inside the quantum framework, they use this proposition as a tool, as a black box, if you want. And also for quasi-neutral limits, so things that are also important in physics. For quasi-neutral limits, derivation of fluid equations, also from second-order systems. So this has been started by Jacobelli and Anquan. And generalized a little bit by Rosenzweig. And there is also a paper by Rosenzweig on the quantum case now. Okay, so always the same proposition. So I'm going to show you a little bit of the ingredients of the proofs, because we have several proofs now for this proposition. But before that, I want to explain how you can treat the Riesz case once you know the Coulomb case. So, how to go from Coulomb to super-Coulomb Riesz. So I've explained a lot of things in the Coulomb case, right? In the Coulomb case, you have the fundamental solution to the Laplacian, and that makes everything very nice in terms of the algebra. So you use the Poisson equation, you use the stress tensor, etc. Well, it turns out that if you have exactly G is a Riesz kernel of this form, when S is bigger than D minus 2, you can twist the problem a little bit to get something very similar to the Coulomb situation. So G is the kernel of a fractional Laplacian. That's not great because the fractional Laplacian is not local. Fractional, so G is the kernel of a fractional Laplacian minus Laplacian. So this time D minus S over 2 is not an integer. So it's non-local, not very convenient. However, there is now a pretty famous procedure that was used by probabilists, I think, for a while, and that was popularized by Caffarelli and Silvestre. Oops. Sorry. Caffarelli-Silvestre procedure, it's an extension procedure, and it allows to get back to a local operator. As long as you agree to add a weight, but with weight. Okay. So more precisely, what you have to do is you have to extend the space in an extended space. So you're going to have to work in RD plus 1. Okay, so you have your space RD that you were working in, and now you add one dimension to it. So what's in RD you call X, and the extra coordinate you call Z. So you have X comma Z. And then you find that G of X, now you write it as G of, so let's call big X equals XZ, so right? So G of big X in the extended space, still 1 over X to the S. And now that's the kernel. Up to a multiplicative constant, it's the kernel of an operator which is local, but which has a weight, and the weight is Z to some power gamma times gradient. So minus divergence Z to the power gamma gradient. So you see it's a divergence form differential operator. Right? So it's divergence of A grad. Right, so it's like if you want minus divergence of A of X grad U, except A of X is this Z to the gamma. And that's for some gamma, which has an explicit formula in terms of S. So some gamma, which is like D minus S plus 1, I forgot. Explicit in S and D, and gamma is always between -1 and 1. Okay, so it could be negative. Okay, so now that you have this representation, the idea is that you want to embed your system into RD plus 1. So everything that was happening in RD, you had points, you had a row. Why you want to see that as a system in RD plus 1. And you want to define the potential generated by a distribution F to be G convolved with F basically multiplied by, I would call this the Dirac mass on RD, which is the uniform measure on RD as seen as a measure in RD plus 1. So in other words, you do the convolution of G with sum of Diracs minus rho delta RD. These points xi, you view them as points in RD plus 1 because you've embedded the space. And now it solves, instead of solving Laplacian H equals this right-hand side, it solves minus divergence of z to the gamma grad H equals some constant depending on z and s times this. Okay, and so now every time you had things like this, g, x minus y, df, df, well, it turns out you can re-express this as the integral of z to the gamma grad hf squared, right, where hf is defined this way. So it's exactly like in the Coulomb case, except you just have to carry over this weight, you see, z to the gamma. It just multiplies everything in your integrals. And this thing is seen as living in RD plus 1. So now, actually, what I wrote there is to be correct. I have to put RD plus 1. So this is an integral in RD cross RD. And here I have to integrate in RD plus 1. And I can also define a stress tensor. Which is going to be, so I had DIH, DJH, well, everything the same except I have C to the gamma in front. So as far as I remember. 2. Okay. So once you have this, you can do the same computations. The divergence of the stress tensor is going to be grad HF times F. That's going to work. You have to trust the sort of algebra, but everything's going to work. And you can start to differentiate the modulated energy, which now it takes this form with the z to the gamma, and re-express everything in the same way, but with weights everywhere. So everything is the same, but with weights. So this is something that we've been using to treat the Rees case for a while now, this extension procedure. So it doesn't create much difference, really, just a few places where you have to pay attention. But that only works in the super-coulombic case. The reason it only works in the super-coulombic case is that this representation with this type of operator is no longer true if f is less than d minus 2. If s is less than d minus 2, you have to take iterates of differential operators of order 2, and that creates some problems. But we have a better way of dealing with that case now in this other paper with Hung and Matt Rosenzweig. Okay, so modulo this story of the weight, I hope you understand that I can reduce to presenting you the Coulomb case. It's enough. The Reese super-coulomb case is going to be essentially the same. And so now I'm going to talk about the Coulomb case for a bit. And what I need to tell you is how to be honestly dealing with these Diracs. Okay, so back to the Coulomb case. So deal with the Diracs. Okay, so there is a sort of technique, a set of techniques that has been introduced in the papers of some of the works we did prior to this topic of mean field limits, works we did on statistical mechanics of Coulomb gases, starting with Sandier, Rougerie, Leblay. So maybe I'll write a few names here. Patlak-Keller-Segel, Leblay, plus myself, all of them, in factor. And it's an idea of a truncation procedure. Truncation or smearing procedure. Okay, so we have these Diracs and we have these potentials minus Laplace, solving minus Laplace H equals up to constant sum of Diracs minus some background measure rho. And now what we're going to do is we're going to look at truncated potentials. So let's call them, so this depends on n, obviously. It depends on n, depends on the points. But let me now put a vector eta. And so eta is going to be just a vector of numbers, eta 1, eta n. So each point has its little eta. And for each point, I'm going to truncate the Dirac, or I'm going to smear it rather, and replace it by sum of delta xi eta I. So where my definition, I need to define this. So I define delta 0 eta. So it's not a power, it's a sort of superscript, to be the uniform measure of mass 1 on a sphere of radius eta. Okay, so instead of a Dirac, you look at a uniform measure on a sphere. Why a sphere? We could take a ball, but it actually makes things easier to do it on the sphere. It's sort of a technical choice, but it's not important. Okay, so this is no longer, it's still a singular measure, but it's kind of less singular. And of course, then delta x eta will be the same, centered at x. Right, so for each, we have all these points, and now we consider, instead of the Diracs, we consider measures on spheres of possibly varying radii. Right, x1, x2, x3, x4, and we have here a radius eta 1, eta 2, etc. Okay, so what we do here is we define h and eta really as g convolved with that. Sorry, h and vec eta. It's defined like this, and it will satisfy the same equation, but with the eta i's here. So the gain in this is that now these functions, so you can notice that the integral of grad h and eta squared, near each point, it's infinite. So it's actually all divergent integrals. near each xi. That's because the integral of gradient g squared is infinite near 0. If you look at what h looks like, well, near each point xi, hn is behaving like g of x minus xi as x goes to xi somehow. And so when you integrate grad g squared in a Coulomb case, you can check it's a divergent integral. And it's the same in the super-coulomb Reese case. It's even more divergent, actually. So this is always infinite. But the integral of grad h and vec eta squared, that's finite. Of course, if the eta i's are positive. Right? So suddenly, these Diracs, these smeared Diracs, they belong to the proper Sobolev space in which you can define this Coulomb distance, right? You remember how I told you the Coulomb distance is like a negative Sobolev norm, really. And these Diracs and the spheres, they belong to that space. So they are accessible, they're admissible, sorry. And so what we are going to write now is going to rewrite the modulated energy in terms of these guys. So another thing I want to say, not only these things are now not singular, is that what's happening when you do this procedure is that you're taking your H, so H, you know, H looks like this, right? It has these infinite peaks at all the points. I'm not drawing very well. You have to imagine these infinite peaks, right? So in dimension 2, it's a minus log peak. In dimension 3, it's a 1 over x. So this is H. And what H eta is going to look like, so this is Hn. This is at x1, x2, x3. What Hn eta is doing is it's doing exactly the same, except it's truncating exactly here. It's doing that and it's truncating here. So where is it truncating? Well, it's truncating exactly at the radius corresponding to the eta you've chosen. This is eta 2, eta 3. And this is exact. So actually, if you take this function, which is the truncation of Hn at these levels, and you compute its Laplacian, you will see that, okay, the Laplacian outside here, that's the same as before, because that coincides with the previous Hn. So the contribution to the Laplacian is only in this part. And in these balls, the Laplacian contribution is 0 because, well, this is flat. So except for this part, let's neglect it a little bit, but 0. And where is the Laplacian? Well, the Laplacian is on the boundary. It's on the sphere, because you have there a jump in the derivative of h, right? So whenever you have a function h and you have a jump of derivative along the boundary, you can expect some contribution to the Laplacian. And what you check is that this contribution to the Laplacian is exactly uniform on the sphere. So it's exactly these smeared Diracs. Okay, so the picture is exactly that. So it's a truncation procedure, or if you prefer, it's a smearing of the charges. And the smearing on spheres makes it nice because it makes it exactly coincide with the truncation. And what's very nice is this way, and this is a proposition if you want a lemma, but I won't prove it, but you can check. It's that H and eta coincides with Hn outside the union of the balls of radius eta. And that's an avatar of Newton's theorem. If you've ever seen that. Newton's theorem says that the potential that's generated by the point charge, or the potential that's generated by any radially symmetric distribution of same mass around that same point charge, these two potentials coincide outside of the support. So here, it means that when you're sitting here and you look at the potential generated by this Dirac or the potential generated by the uniform measure on the sphere, seen from here outside, they're the same. That's Newton's theorem. And this is exactly, if you translate this for these functions, it says exactly that these two functions coincide. Okay, so this is just to have a good representation of these truncated potentials. And now let me rewrite the modulated energy. So remember, now we're not dealing with any dynamics, anything. This is purely functional analysis. So we're given points and we're given distribution rho. And we're just going to rewrite Fn, Xn rho, which was defined like this. Gx minus y, sum of Diracs minus rho, d sum of Diracs minus rho, on the complement of the diagonal. Okay. So now let me say this. I want to replace these things by things that are smeared at radius eta I. So I'm going to think of eta I very small. So I can certainly say that this is true when all the eta i's go to 0. This thing recovers that thing, and I should put truncated away from the diagonal. But now nothing prevents me from putting back the diagonal and removing it. So I'm going to write eta I going to 0, all eta I is going to 0. I'm going to put back the diagonal. Back the diagonal. Okay. The reason why I can put back the diagonal is because now these things are no longer singular. When I hit delta xi eta I with itself in G, it makes a finite term. But I have to subtract all the terms that I've added here, which are, so I have 1 over n squared, and I have delta xi eta I of x, delta xi eta I of y. Right, so it's the same index I. So I hope you agree with this. And now let me write what this thing is. So this thing, I claim that by translation invariance is the same as if xi was 0. You know, everything centered near xi, I can shift everything back to the origin. Then I can scale everything. And then I can say it's the same as if eta I was equal to 1 up to scaling. So I'm going to find myself with g of x minus y, delta 0, 1, delta 0, 1 of y. And then it depends on I have to do my little change of variables. Or let me not do it this way. Let me not scale. It's easier. So I'm just going to compute integral of g of x minus y, delta 0 eta of x, delta 0 eta of y. So I have to do a convolution of the Coulomb kernel G on the sphere of radius eta. But now I remember Newton's theorem And I remember that this coincides, so G convolved with delta 0 eta coincides with G convolved with delta 0 outside of D 0 eta by Newton's theorem. And what is G convolved with delta 0? Well, that's G. Okay. So this is all equal to what? This is all equal to G of X delta 0 eta of X. Because once I've done the convolution, this thing is supported on the boundary of this ball. And on the boundary of this ball, they coincide. So I can just replace it by G. Okay, so now the integral of G delta 0 X, that's the average of G on the sphere, but G is radial. So this is just G of eta. G is radial. Okay, so I'm doing a little bit of abuse of notation here. I hope it won't shock anyone, but I'm confusing G, which is a function of a vector, with a function of a scalar here. Right, so G is radial. Right, so G is like this. But I can also see it as a function in 1D. Right? So this is G of R. So now G of eta is the value I get for any vector of norm eta. Oh, so it's just simply, if you want, it's 1 over eta to the S or minus log eta. Okay, so what did I do here? I rewrote the modulated energy as a limit of a term like that, and some explicit terms that I can subtract. So let me rewrite this. F and X and rho is the limit as eta I, all eta i's go to 0, dx minus y, 1 over n, sum of delta xi, eta I minus rho, right? Minus, so I had a 1 over n squared, and I have the sum, so 1 over n squared, sum from 1 to n of g of eta I, with this abuse of notation. Okay, so you see that as eta I goes to 0, you expect these double integrals to blow up. Well, because we know that here, once the diagonal has been reinserted, this should be very, very large. It's divergent if eta is 0. But we are subtracting these terms that are getting very large as eta I goes to 0. So this is a renormalization procedure. This is a renormalization procedure. You have you have the difference between two infinities, essentially. Right? So you have the difference between one term that's going to plus infinity and another term that's going to plus infinity, but they're actually going to infinity in the same way. And when you subtract them, you get something that's that remains bounded as eta goes to 0. And now the good thing is that with the formulation for the first double integral, I can rewrite this now. Rewrite first double integral as the integral of I can recognize G convolved with 1 over n sum of delta xi eta I minus rho multiplied by itself. And what is this? This is what I defined as Hn eta. And what is that? That's minus Laplacian up to this constant 1 over ct. It's minus Laplacian of h and eta. Okay, so now I can do legitimately what I had been doing in the regular case when dealing with the limiting distributions that are smooth, you know, that are bounded. I can actually integrate this by parts, use Green's theorem, or Green's formula. Green's theorem. And rewrite this as the integral of 1 over CD integral of quad h and eta squared in RD. Now remember, if you were in the Rees case, you would add here, you would stick in here these weights, right? That's all that would change. But here, since we're talking about Coulomb, I don't put the weight. Okay, so Fn, well, that's my formula. Fn, xn rho, this is an identity. This is the limit as eta I all go to 0. 1 over CD integral of quad hn eta squared minus 1 over n squared sum of g of eta I. So at this point, it's not yet clear why I bothered to use different etas for the different points. You could use the same eta for all the points. You could put 1 eta, let it go to 0. And here you will have just 1 over n times the same term. And you see this is this formula of renormalization. Formula. It allows to give a good meaning now to these formulas that involve the Dirichlet energy of the potential. So what you have to do is you have to take the potential but truncate it properly and subtract some proper divergent term. And then this all makes sense. So this is an identity. So that's the starting point, but now we can play with this. And the idea is to play with changing the values of eta I. Okay. So there is a proposition that I will not prove for you, but just give you maybe a vague idea. Here's the proposition. It's hard to frame it. So the proposition is essentially a monotonicity property. So it's almost, it's not an exact monotonicity, but it's almost monotonicity in eta I. And it says that if you compare 1 over CD, the integral of quad h and alpha. So I'm going to change eta, right? So go from eta I to alpha I or alpha I to eta. Compare this and that and that. So the same quantity with another eta. I'm going to take the opposite way, like this. Plus an error, so I told you it's not exact. But the error is proportional to 1 over n sum of alpha I t minus s. So the alpha I here are going to be assumed to be bigger than the eta I. Okay, so this is true for each alpha I bigger than eta I. So for any configuration, if alpha I is bigger than eta I, this is true. And I would say with equality, if and only if the balls B, xi, alpha I remain disjoint. Okay, so we have these points, x1, x2, etc. So we start from balls of radius eta 1, eta 2, eta 3, and we increase them to balls of radius alpha 1. So we'll try to do it in such a way that the balls remain disjoint here. Alpha 3. Then if I compute it with respect to these balls or respect to these balls, you see I sort of approximate my modulated energy in this way or in this way. I don't change very much the result. So the error that I make here is going to be quite small. As soon as the alpha I remain small enough. And if you wanted to start to have overlapping balls, so if the alpha i's were growing so much that the balls started to overlap, you would still keep an inequality. So there would be a change, but the quantity you would compute, so I have it the wrong way. Sorry. It would only decrease the energy. So it's this way. So what is this all saying? You have to remember Newton's theorem, right? Newton's theorem is saying that if you have charges, they interact. If you replace the charges by radial charges around them, as long as the balls don't overlap, it doesn't change anything. So the interaction doesn't change, in fact. If you increase the size of the balls so that there is overlap, your charges will interact now in a different way. The value of the interaction will be different. It will actually be lower. So in other words, the repulsion between 2 points is larger than the repulsion between two overlapping, possibly overlapping spheres. Right? So by smearing, you're only decreasing the repulsion and decreasing the interaction. What creates an error is the background rho, because then when you smear, when you inflate the ball, you change a little bit the interaction with rho, because there's interaction between the points, interaction between the points and rho, and that you're changing a bit. And this is why you have this price to pay, and this O, actually, this low O depends on the L infinity norm of rho. Okay. So now, what that means, the corollary, now if you let eta I be very, very small, going to 0, we find 1 over CD, integral grad H and alpha. So it's all integrated in RD. Okay. This squared minus 1 over n squared sum of 2 alpha I. This is going to be less than f Fn, x and rho, because just because this thing, as eta I goes to 0, that converges to Fn. That's this formula. Okay, so I can write this, it's less than Fn, plus maybe this error, plus O of 1 over n sum of I equals 1 to n of alpha I d minus s. And so now apply to alpha I equals n minus 1 over d. So why do I choose n minus 1 over d? Because when you have n points in a compact set, that thing is the typical scale of interdistance between the points. The typical interdistance between points in RD, right? So you have n points in RD. Each of them occupies a volume 1 over n. So the length scale is n1 minus 1 over d. And when I do that, I find f n x n rho is bigger than something positive. So I can throw it out. And here I get minus 1 over n g of n minus 1 over d, right? Plus O of, so here I get n minus 1 over d to the d minus s, so that's s over d minus 1. And there's n of them, and divide by n. So if I did it properly, I should find exactly the same order of terms. So let's see. So if we're not in dimension 2, g is just the power d minus 2, so 2 minus d. So it's 2 minus d minus 1 over d divided by n. And here I have n s over d minus 1. And s, I said, is d minus 2, sorry. So s. So you can do this for Reese, it's the same. Or maybe I should do it with Reese. Minus, so it's s over d divided by n. And s over d minus 1. So you see that I've balanced the terms in such a way that I define similar order s over d minus 1. Okay, so why did I pick this interdistance? Because if I pick something smaller, then this term is going to be even more negative. That's not very good. And of course, this term would be better, it would be smaller, but this minus s is always positive. So this term prefers alpha I to be small. This term, to have a small error in the lower bound, prefers alpha I to be large. So when one prefers one to be large and the other one prefers to be big, you just should balance things by making them equal. And so in fact, you check that this choice is exactly what makes those two terms of equal order. And now we found the optimal lower bound. So this is a general fact that we have found. It's corollary. For every configuration of points and rho, which is a bounded density, this modulated energy is bounded below. So you remember I told you it's not a metric. It's no longer a metric. In particular, it loses positivity, but it doesn't lose it by very much. It's still bounded below. That's a general fact. And this order is actually fairly small. So this is because S is strictly bigger, strictly smaller than D. Remember, S is strictly smaller than D, so S over D minus 1 is actually negative. So it's bounded below by something extremely small. So it's not far from being positive. Okay, so that's just an illustration of this. And another corollary I want to write, so it's not immediate from what I've written, but I will just write it as a statement, is the following. So when you do these truncations, you want to keep your balls relatively small. Why? Because you don't want to distort the energy too much. So you want in particular to stay in the equality case. So to stay in the equality case, you want the balls to be not touching. You want the balls to be disjoint. So that's one thing. On the other hand, you also want the balls to be fairly large, so that this term that you're throwing away, the positive part that I threw away here I threw away this positive grad hn alpha squared. You want it to be the smallest possible, because if you're going to throw away something, you want to throw away something small. And the smallest possible is when the things are actually the most inflated. So the balance between those two constraints is actually to take the radii to be exactly the minimal distances. So the largest possible balls, so that they remain disjoint. The largest possible balls, so that they remain disjoint. Is to choose theta I equals what I define as Ri. Ri is defined as the mean for a given xi, the mean to distance to the other points, right? But maybe we're going to divide it by 1/4 in order to be sure that the balls are disjoint. So I'm going to do this. And I'm also going to max this at n to the -1 over d. So mean of this and -1 over d, because that's the typical length scale where we expect our distance between points to be. So in case points happen to be very isolated from everyone else, we will still max it out at that distance. Okay, so we define Ri this way. And with this choice, actually a lot of things are convenient. And we have this proposition, which is this. So the sum of G of Ri I have to divide by n squared, I think. N squared. It's bounded by, yes, sorry, by the way, I didn't mention, but when S is 0 here, so if S equals 0, which is the log case, you have to pay a little bit more attention. You're going to get a log term, but it's still okay. So you should treat this separately. Okay, so now we're going to be able to bound by this plus 1 over 2n log n. That's in the case where we're in this Coulomb case, S equals 0, D equals 2. So I write it like this. I write indicator of S equals 0, D equals 2. That corresponds to a term that only exists in the logarithmic 2D case. So if you want in the 2D Coulomb case, I have a log term. Otherwise, it's not there. Write it like this. And this is this plus some errors, which depend on the norm of mu. This can be optimized a little bit. And then you have this S over D minus 1 that I wrote before. Okay, so this is that. And second point in the same proposition, and then I will stop. is that the integral of grad h, and with the vector of parameters now chosen to be the Ri, that is bounded by C times the same thing. Okay. So let me just explain what this means, and then I'll stop. So here you recognize your modulated energy. In the log case, you have to subtract to it a fixed term. So in fact, you should really think in the log case of these two things together as being the right quantity. But otherwise, don't worry. Now remember that because the balls are disjoint, the modulated energy can be seen as the difference between this term and this term. And this is the formula that's above. So let me go back. You see here you have equality when you have a limit. And here you have an inequality. And here I should have added with equality. Right, I should have added with equality if the balls are disjoint. But with my choice of alpha I equals Ri, I've chosen the balls to be disjoint. So now I have equality. So F is equal to this difference between these two divergent terms. I told you it's about this renormalization. You have a very large term and a very large term, but you have a cancellation between the two. Now, what's interesting is when you choose alpha I to be Ri, then each of these two terms separately becomes controlled by the energy. Right? So even though the energy is the difference between two terms that go higher and higher, if you stop, if you don't make alpha I too small, if you make it large enough, if you make it equal to Ri, then each of the two terms that are subtracted from each other becomes controlled by the difference of the two. So you can control them separately instead of controlling the difference. Okay, so we can control integral of grad h and r and 1 over n squared sum of g of Ri separately by Fn instead of controlling their difference. These are sort of the two main tools. And then tomorrow I will show you how, with these estimates, how you can finish the proof of this commutator estimate. So, but this is really the sort of technical ingredients. You can find them written, I would say, in the simplest way in my paper in Duke, but there are some rewritings also in the more recent papers, but I think it's readable there in the simplest way. I'll take questions if there are any. No?
Is there some questions?